Hello, my friends, data crew, data analysis, data scientists. Today I'm going to present to you a functional form model with real world data sets. A functional form in sometimes theoretically plausible as well as practically much more helpful in adjusting the deficiencies in revising the insights from a linear functional form model. So that to prove that case, I'm going to show you how transforming a model can improve on the precision of the model of the linear regression model that has given. So here I have the real world data of Fortune 1000 companies in which I have the columns as ranking of the companies in the shape, in the size of the company revenues, the sector, industry, and other quantitative columns like revenue, profit, and employees. The ordinary least squares linear model was run on these, and we found before running even, we can see the histograms of revenue, profits, and employees model, none of them showing a bell-shaped curve, all of them showing a skewed curve. So once we run the linear regression model, OLS, on profits as a function of employees, revenue, and rank, we found out that the explanatory power of this model is very low, less than 40%. And the model has a big problems of AIC, archaic information criteria, and BIC, Bayes information criteria. Very large numbers in thousands, 18,000, 18,500 in those numbers, making the model not suitable. Smaller than AIC, BIC numbers, that model is preferable over the larger AIC, BIC numbers. And the conditional number showing much bigger numbers like 25,600, 250,600, that kind of number, showing large numbers of multicollinearity problems among the predictor variables. So these problems, when looked into the pictorial forms, you can see here all the residuals versus fitted models all clustered as a funnel shaped. So not homoscedastic. They have a heteroscedasticity problem. The residuals are supposed to be distributed evenly, but that's not the case here, funnel shaped. Similarly, if you look at the normality assumption, you can see it has been violated by looking at the QQ plot, no clustering around the diagonal. The shape of the QQ plot is S-shaped, so that violates. That suggests that normal function, linear function is not suitable. Quadratic or other kind of function is required. And the histogram also showing this long tail as well as long peak as well as tails spread on both sides. So showing great kurtosis and skewness. That means causing imprecision in the measurement of the models. Hence, we have these problems already seen. So what does that mean? Should we just toss that model out? Should we just give up and say that this is not measurable and we cannot do any explanation of these behaviors? No, we can look into the functional form of the model. The world does not run in linearity every time, everywhere. There are at some points accelerations, some points decelerations, some exponentiations, all these kind of things, not linear all the time. So for that purposes, we can check if any other forms of functions improves on those problems that we have shown above. So one such attempt is log normal model. If you log both predictor and response variable, that is called log or log normal model. If you only log the predictor variable, the response variable, that is called loglin model. So here we are going to look at the log model, that is log normal model. So let's start with that. So for that, plt dot, let me just, first we should change the model into log before running any regression. Okay, so for that we're going to start with log df equals df dot copy, that is our original model. We're going to copy so that the original model is not contaminated, is not affected by these. And then now print, we're going to find out which are the zero or non-negative variables that would, if they persist, that would cause problem with the log transformation. So first, to find that out, let's do print f. Okay, min. So we're going to find out min employees. Min employees is going to be log df access the employees column, employees variable. So column and variables are interchangeably being used. Okay, that dot min. We're going to find out the minimum values, which will indicate that there are non-negative values as well. So for same for the next variable, which is min revenues, min revenue log df. Let's make that revenue here dot min. Similarly, let's go for the profit. Okay, min profit is going to be profits. The variable is profits min. Okay, so we have these to identify where are these min values. Okay, once we identify, then we can remove those mins. So let's run it. Okay, here is some name. df is not okay. Let me run the kernel because df is not defined because of kernel not being refreshed. Okay, so we see there is a min profit negative value and min revenue has some, min employee has some. So for that, let's remove those negatives. Okay, so that we can have only non-negative values. So log df equals log df. We're going to access the variable log df times employees is greater than 0. Similarly, and log df is going to be revenue, not small, revenue also greater than 0, is non-negative, and the last remaining is log df axis profits is non-negative. This is how we are removing all the negative values and non-zero values. Okay, so that will remove those. And now let's create the columns that has these log variables. Okay, log df, and the column name is going to be log employees log employees equals np dot log df employees. Okay, similarly we're going to have log revenue here is going to be here is going to be revenue, so we're going to do that. And another variable is log profit is going to be profits. Okay, so now we have transformed into, we have created these columns which are log transformed. Let's now print the log df dot head. Okay, let's just check first 5 rows with the transformed. Okay, you can see this is just a warning. I am not bothered with this for now. Try using .log instead of value instead of that. So what it is saying that is here we should use .log, but just be as it may, and we can clearly see now that here you can see those columns are created: log employees, log revenue, log profits. Okay, now log regression, we're going to run log regression equals smf.ols formula equals quote profits equals log profits, log profit, make sure I'm writing the correct log profit. Yeah, okay, log profit connected by tilde to log employees plus log revenue. Okay, log revenue, comma, data equals log df, data equals log df dot fit. Okay, let's print the numbers. Print f log normal regression results Okay, let me write that. Log reg dot summary, call it, and close that. To show this in the next line, let me just write this here. Okay, so let's run this model. If I did not make typos, it should produce the results. Okay, here we see the results. Now compare this result with the previous result. Previous result we had 0.96 r square, here 0.508 r square, so much improvement. And before we had large conditional numbers like 25,000 something. Now here 118. It is still a problem. 118, any conditional number greater than 100 suggests severe multicollinearity problem. Acceptable is less than 100. But you can clearly see the number has been brought down much more from the thousands of large numbers into 100. Similarly, if you look at the AIC and BIC, these two measures are used to select among the models which one should be chosen. AIC, archaic information criterion, has now come down to 2400. Before it was 18,500 something. Okay, and BIC, Bayesian information criterion, has also come down to 2450. Before it was 18,500, 900, like that kind of information. So there is also improvements. And the errors of committing type 1 error in earlier models, in linear models, we had type 1 error was for intercept 22.8%, for really large number. Whereas in this model, the chances of committing type 1 error in the intercept has vanished. It's 0, very, very small, 0%, 0, 0, 0. You look at the p-value, p-value shows you the chances of making type 1 error. Type 1 error means accepting the null hypothesis that beta sub 0, which is a representative of intercept, equals 0. Accepting that when it is not true, that is type 1 error. Rejecting that when it is true is type 2 error. So here we have reduced the chances of accepting the hypothesis, the estimation of intercept equals 0. Now it's not. That imprecision, that rejection, committing type 1 error has gone. So, and similarly, we have shown log employee significant and log revenue also being significant in that. So, number wise, as well as we can clearly see the difference. Now let's see these, if pictorially we can see these differences. Okay, for that I am going to start with homoscedasticity check. Okay, homo check, okay, means residuals against fitted values are evenly distributed. Okay, so how many t's are here? A lot of t's. Let's make it down. Evenly distributed. So we're going to check that first. Let me make it a markdown. Okay, so make it a markdown. Shift enter. Okay, so let me plot that plot first, and then we'll check QQ plot and other things pictorially. Okay, so plt dot figure big size equals 10, 6, and plt dot scatter, because we're going to excuse me, we're going to plot fitted value against residuals, log reg dot fitted values, comma, log reg dot resid alpha equals 0.6, comma, color equals, let's green, edge color equals black. Okay, that is the setup of the picture of the histogram of the plot, scatter plot. plt dot ax h line, horizontal line, we want to distribute the residual plots at x equals 0. Okay, 0 equals color equals, let's make it yellow line, line style equals, let's make it dash dot, and line width equals to a little figure. Okay, plt dot title, let's set the title residuals plot log normal model. Okay, that will be the title. Okay, so make sure you are seeing this. I tend to forget that. Okay, PLT that residuals, and let's put PLT dot type layout so that none of the labels are cut off. PLT dot show. Okay, now let's watch this and compare this with the linear model. This is log linear model. We'll compare this with the linear. Shift enter. Okay, now you can see, look at these residual distribution. The dots above the line and below the line are of equal number. If we take the sum of the dots above the line and the sum below the line, they will amount to approximately to 0. So this is called alleviating the heteroscedasticity problem. You can see the residuals must be homoscedastic, can be achieved with this, can be seen with this plotting. There is no clustering, there is no funneling of this dots. If you look that above with the normal, you could see easily, look at this funnel size there. So that's a big improvement over the model. So how about the improvement on the QQ? Is there any improvement on the QQ? Normality assumption? So let's check that out as well. So we're going to check normality of residuals with QQ plot and histogram side by side. Okay, so let me just make it a markdown so that you can see it markdown. Okay, shift enter. Okay, so now let's write a code for this. So let's do this. Fig, comma, AX1, comma, AX2, because we need two plots side by side, that's why I had to do this, equals plot that subplots 1, comma, 2, comma, big sides equals 12, comma, 5. Okay, that is the setup. Now, QQ plot. So how do we get QQ plot? We get QQ plot from SciPy stats model. Stats dot prob plot. So what are we getting? Log reg dot resid. Okay, distribution equals normal, and plot equals ax1 dot set title. What will be that? QQ plot of residuals. Okay, so before I write the histogram, I would like to see this. For that, I'm going to do plt.tight layout, plt.tight layout, plt-show. Okay, let me see this. Okay, now you can see, look at this. It is much more points are clustered around the diagonal than before. Much improvement. You can compare this with S-shaped curve here. You can clearly see it's an improvement. Now, let's write the histogram as well. ax2.hist log reg dot resid, comma, color. So what color would you like this? Let's make the color orange color, comma, bins equals, let's make 30 just before 30, edge color equals black, and alpha equals 0.6. Okay, that is the setup. ax2 dot ax horizontal line, no, vertical line, because it's just, this is a histogram. V line, vertical line, is going to be 0 at x equals 0. And color, so what color would you like? Let's make this also yellow. Line style is going to be dot dot, comma, line width is going to be 2. Okay, now ax2 dot set title is going to be histogram of residuals. Okay, residuals, log model. Okay, so let's go for ax2 dot x label, set x label. X labels are going to be residuals. Y levels will have frequency. ax2 dot set y label is going to be frequency. Okay, so that is about it. So let's run it and see. Okay, now you can see, look at these, well-saved distribution of residuals. Okay, so this also establishes, that improves on the fact that, look at the previous distribution, this massive skewness and kurtosis, and now you can see this much improvement on that. We have improved greatly into this. This way you can see clearly that functional transformation is one of the tools the data scientists can employ before deciding just to chuck out the linear model, the linear regression function. We can see if we can transform the model, because in practical life, linearity is not always available. The practical life, there are quadratics, there are exponentials, there are reciprocals, polynomials, all these kind of mathematical possibilities. That's why we need to employ this transformation. So for the first step towards that was this log linear model, where both the predictor as well as the response variables have been transformed. By doing so, we have been able to improve the skewness, the problems of multicollinearity, the problems of heteroscedasticity. We have been able to improve. This way, we can say that in real world data, a data scientist can do much more objective assessment with his or her strength of recognizing that linearity is not always available. We have other functional forms. So I hope you like this and you will continue watching this channel, subscribing my channel, watch my tutorial to learn all about data science, statistics, and data analysis with Python, Pandas, and NumPy. You get the benefit here of statistics as well as economics, which in other words, this is econometric measurements that I have displayed to you. This is how economists achieve the blue properties of a regression analysis. Blue, best linear unbiased estimator. This is how it is achieved. So thank you for watching. Please subscribe my channel. I will present you more such lessons in the coming days. Thank you for now. Bye bye.